Okay, so section 6.5 is about applications of some of the stuff we've been doing with exponential functions, and in particular about exponential growth and decay. You need to read or at least skim the book, because I'm not going to talk about the theory behind things. This video is just an example, so that you can see an example of how to do problems like this and work on homework problems. So, read the book first. Okay, we're going to be doing problem 13 from the exercises in the book. And it says a roast turkey is removed from the oven when its temperature is 185 degrees Fahrenheit and it's placed in a 75-degree room. The first thing they want to know is, if the temperature of the turkey has cooled to 150 degrees after 30 minutes, what's the temperature after 45 minutes? Okay, so different things cool down at different rates. A turkey is pretty dense and pretty heavy, and so it probably takes a long time to cool. If you put a single French fry at 185 degrees in a 75-degree room, we would not expect it to still be 150 degrees after 30 minutes. It would cool down much quicker. So the turkey is cooling at this particular rate. There's also something else going on. The rate at which something cools depends on its density and mass and specific heat and all those things, but it also depends on how far away its temperature is from the surrounding temperature. So something that's only a degree warmer than the surrounding temperature is going to cool more slowly than something that's 100 degrees warmer than the surrounding temperature. Newton's law of cooling expresses this. So what it says is dt dt equals k times t minus ts. Now what does that mean? Capital T is temperature of the thing, right? In this case, the turkey. T sub s is the temperature of the surroundings, the ambient temperature. So T minus T sub s over there on the right is the difference in temperature between the thing that's cooling and the environment around it. Okay. Then there's this constant K, which is the thing that depends on the mass and the density and the specific heat and the surface area and so on of the object cooling. So it's different for different objects. And little t is time. So what does this equation say? It says the rate at which temperature changes is some constant times how much warmer it is than the rest of the room, or how much cooler it is than the rest of the room. So some constant times the difference in temperature between the object and its surroundings. So that makes sense, right? You have this constant that depends on the object, and then you also depend on how far away your temperature is from the room temperature. So we're going to change variables and let y equal temperature of the object minus the temperature of the surroundings. Temperature of the surroundings is a constant, so this is just a change of variables that is subtracting a constant. Okay. Then when you take the derivative with respect to time of y, that would be the derivative of temperature with respect to time minus the derivative of this surroundings temperature. But since that's a constant, its derivative is 0. So the derivative of y with respect to time is the same as the derivative of temperature with respect to time. So that means dy dt is the same as dt dt, which we know from the previous slide is k times this difference in temperature, but that's just y. So we have the derivative of y is proportional to y itself. dy dt equals k times y. K is some constant, so this is a proportionality thing. So the bigger y is, the faster it changes. The smaller y is, the slower it's changing. This differential equation, a differential equation is an equation that involves derivatives. This differential equation has a general solution, and we'll see that in a minute. But right now, we want to point out that the surroundings temperature in this problem is 75 degrees Fahrenheit. The initial temperature of the object is 185, which means the initial y value is T minus Ts, so that's 185 minus 75, so that's 110. And the general solutions to the differential equation that we've got, dy dt equals ky, general solutions look like this. Y, which is a function of time, y of t, equals the initial y, y of 0, times e to that constant k times time. So y equals initial value times e to the kt. That's the general solution. our initial value, y of 0, is 110. Y of t is something that changes with time. That's the y value at each point in time. K is a constant. We don't know what it is for our turkey, and t is time. Little t is time. Okay. But we are given information about what happens at 30 minutes into this situation. So after 30 minutes of cooling, t equals 30. We can write the equation like this. Y of 30, right, the y value at 30 minutes, is equal to the initial y value, 110, times e to the kt, but t is 30. Right, so I replace t with 30 and the initial y value with 110. And I want to point out that we're measuring t in minutes. You could measure t in hours. That would change some intermediate steps, but you should get the same final answer. Okay. And what is y of 30? Well, at 30 minutes, the temperature, capital T, of the turkey is 150, minus that 75-degree surroundings temperature. So y of 30 is T of 30 minus TS. So 150 minus 75, that's 75. So I can divide both sides by 110 and get 75 over 110 is e to the 30k. Take the natural log of both sides, and I get the natural log of 75 over 110 equals 30k. And then divide by 30 and get k equals negative 0.01277. So we have found this constant k that is the constant that is specific to our particular turkey that we removed from the oven. Okay, that still hasn't answered the question. The question was, what is the turkey's temperature 45 minutes after you take it out of the oven? But we used the 30-minute data to find k. So at t equals 45, remember we have y of t equals y of 0 times e to the kt. Now we know what k is, and we can plug in t equals 45, and we will find y at 45 minutes. It's approximately 62. I rounded. So y of 45 is 62. What does that tell us about the temperature at 45 minutes? Well, remember y is just the temperature minus the surrounding temperature. So T of 45 minus the surrounding temperature is 62. That surrounding temperature was 75, so the temperature of the turkey at 45 minutes is 137 degrees Fahrenheit. Okay, so we used the given data to find K in this particular situation, and then we put that back in along with T equals 45 to find the temperature at 45 minutes. The second part of the problem says, when will the turkey have cooled to 100 degrees Fahrenheit? Okay, so we know at 30 minutes it was 150, at 45 minutes it's 137. How long will it take to get to 100? Well, a temperature of 100 converts to a Y value of 25. So we want to know what little t time value would make the y value 25. We can plug into our equation. 25 is the y value. Initial y is still 110. K is still that negative decimal. And this time t is the unknown. I did all the steps at once. We solved for little t, and we get about 116. So the temperature will be 100 degrees Fahrenheit after about 116 minutes. Okay. So that's how you do this type of problem. The same ideas are good for cooling and heating, good for population growth and decay, good for radioactive decay, lots of different applications of exponential growth and decay that come from differential equations where the derivative is proportional to the value. I hope that this has been helpful, and good luck on the homework.